Assalamualaikum warahmatullahi wabarakatuh. My name is Syafiqah binti Suhaimi, and I will explain about additional theory for this experiment, deflection of cantilever beam. So, the deflection of a cantilever beam is essentially a three-dimensional problem. The deflection and stress distribution in a long, slender cantilever beam of uniform rectangular cross-section made of linear elastic material properties that are homogeneous and isotropic. Cantilever beams have one end fixed, so that the slope and the deflection at the end must be zero. To calculate the deflection of beam can be used Macaulay method. Macaulay method is a technique is very convenient for cases of discontinuous and discrete loading. The application of a double integration method to a beam subjected to a discontinuous load leads to a number of bending equations and their constant. The derivation of the deflection curve by this method is tedious to say at the least. Deflection, also known as displacement, can occur from external applied loads or from the weight of the structure itself and the force of gravity in which this applies. The unit of deflection is a length unit and normally taken as millimeter in metric. This number defines the distance in which the beam has deflected from the original position.
Assalamualaikum, my name is Hanani, binti Halim, DEFLECTION, and I will be presenting the result and observation for this experiment. This is the result for our experiment. According to this result, aluminum experiences the least deflection compared to the other two specimens. We can also see that mild steel has the highest deflection compared to the other two specimens, despite having the highest value of Young's modulus between the other two specimens. Aluminium experiences the least deflection, despite having the lowest Young's modulus, is mainly due to the high value of thickness that it is given. The value of thickness is used in calculating the second moment of inertia, or I, and the value of I is then used to calculate deflection. Deflection has an inversely proportional relationship with I, hence, having a bigger thickness contributes to having a bigger I. Having a bigger I, then, influences the deflection in a way that a bigger second moment of inertia will result in a lower value of deflection. While conducting this experiment, we need to reset the dial gauge to 0 upon every loading and unloading. Upon resetting, we can see that the value of 0 in the dial gauge does not stay or fluctuates. This may lead to systematic errors. Some real-life application of cantilever beam would be balconies, traffic lights, aeroplane wings, shelves, cranes, and many others.
Hi, my name is Nurul Hidayah Natasha binti Zainuddin, and my matrix number is TD180049. Today, I am going to explain about calculation. The formula given for deflection is L to the power of 3 divided by EI times W2 per 384 plus W minus 8 times W2 per 192. And the formula given for W2 is equals to W times 5 divided by 16. For sample calculation for brass when load is equal to 5 Newton, we get the value for W2 is equal to 1.56 Newton. So we enter the value into the deflection formula. Then we get the deflection value for brass when load is equal to 5 Newton is 0.000395 meter. As the sample calculation for aluminium, when load is equal to 5 Newton, we also get the value for W2 equals to 1.56 Newton. When we enter the value into the deflection formula, we get the deflection value for aluminium when load is equal to 5 Newton is 0.000272 meter. Lastly, Sample calculation of deflection for my steel when load is equal to 5 Newton, we also get the value for W2 is equal to 1.56 Newton. Then we entered the value into the deflection formula. We get the deflection value is equal to 0.000693 meter. Next, we have to calculate the gradient of the graph. The formula given for gradient of graph is y2 minus y1 divided by x2 minus x1. The gradient of graph for brass is equal to 12469 Newton per meter, and the gradient of graph for aluminium is 18382 Newton per meter. And lastly, the gradient of graph for mild steel is equal to 7215 Newton per meter. Next, we are also asked to calculate the value for Young modulus of elasticity. The formula given for Young modulus of elasticity is ml to the power of 3 divided by 192 times I. So, for brass, the value of Young modulus of elasticity is 81.79 gigapascal, and the value of Young modulus of elasticity for aluminium is 52.23 gigapascal. And lastly, the value of Young modulus of elasticity for mild steel is 156.79 gigapascal. And lastly, we are asked to calculate the percentage difference. The formula given for percentage difference is equal to E theoretical minus E experimental divided by E theoretical times 100. So, the percentage error that we get for brass is 25.65%, and the percentage error for aluminium is 25.39%. And lastly, the percentage error that we get for mild steel is equal to 25.34%. That's all from me. Thank you.
Good morning, my name is Nazatul Syafiqah binti Rozi, DD 180089, and today I'll be presenting the discussion for the deflection of cantilever beam experiments. As for the discussion, we can see there are 4 graphs here, which are the first one is the load versus deflection for experimental value, and the other 3 is the load versus deflection for each specimen comparing the theoretical and experimental value. From the first graph, we can see that the material used are aluminium, brass and mild steel. From the line constructed, we can say that the least deflection is experienced by aluminium. This is because aluminium has the thickest thickness of material among all, and that makes the material is more stiffer than brass and mild steel, even though it has the lowest value of Young's modulus. But for the maximum deflection is experienced by mild steel. Mild steel has the thinnest thickness of material, even though it has the highest value of Young's modulus, and it also affects the deflection of the beam. For the second graph, which is the load versus deflection for brass specimen, we can see that the experimental give the positive value and the theoretical give the negative value. But however, the value is not has too much difference. And for the third graph is the load versus deflection for mild steel aluminium, which is also same as the previous graph, which is the experimental give positive value and the theoretical give negative value. And for the last graph, the load versus deflection for mild steel is also the same, where the experimental give positive value and the theoretical give negative value. But however, the gradients of both lines is quite different. This is because theoretical usually does not consider the thickness of specimen, and as we know that the highest value of Young's modulus usually will give the lowest risk for the beam to deflect. But in this case, mild steel has the thinnest thickness among all, and it shows that the higher value of Young's modulus is not the main factor in avoiding deflection, but the thickness might affect the value of the deflections. And for the last part is the importance of knowing the characteristic of engineering component. And the first point is to lessen the risk of failure. It is important to know the mechanical behavior of the component because wrong material might affect and give some failure to the design that lead to fracture for the product. It is important for us to know the mechanical properties so that we can fit the requirements needed and can suit the desired performance. And for the next point is to upgrade the properties. As an example, if a material need to go for heat treatment process, we can do the heat treatment process as example to harden the material so that it will give the maximum performance. It is important to make sure the output will not yield to any extreme condition and can perform well in any condition so that it can give the best performance for the process. That's all from me. Thank you.
Hi and Assalamualaikum. My name is Syed Muhammad Zulfahmi bin Syed Zawawi and I am from Group 4F for Lab 6. Okay, today I'll be presenting about the conclusion of the experiment. From this experiment, we can conclude that the objective of this experiment have been achieved, although the data value obtained was slightly different because of errors. All graphs in linear positive straight line graph. The error caused and influenced the result of this experiment, although the value is small, but it shows big gap in graph. For the Gauss value starting with 0 before the experiment being conducted. Data gathered having different in value because of error. Observing error occurred while taking the reading of the experiment. It is caused by inaccurate point when taking the reading, and observer pressed the beam that caused the change of reading. Besides that, the condition of the experiment itself, which is very sensitive to pressure, will lastly result different in value taken. To overcome those errors, observers should take the reading repeatedly and then take the average data. This experiment must be done in stable table and make sure the apparatus in a good condition, while the one conducting the experiment must handle it carefully to prevent difference in pressure of the reading taken. Okay, that's all for me for the conclusion. Thank you.